Excellent. Hi, everyone. I'm Omar. I'm with Vivi here. You already know him. Today, we're going to talk about TTS. It will be a TTS deep dive. Vivi will start off the presentation today, and then Batsal will join us for the second part of the presentation. And as always, at the end, we'll spend some time answering any questions that you might have. Just to answer, sorry, to give like some quick details. If you're watching us from YouTube, at the bottom, you can find a link to the forum. In the forum, you can ask any question that you might have. And as always, we'll spend some time answering each of these questions in detail. Additionally, after the session, we normally share additional resources, additional links, papers that you can later on use as well. Also, you can join the Discord. We have a channel there if you want to join some of the discussions that are happening over there. And finally, we have a GitHub repository. In this repository, we are uploading the slides, Colab notebooks as well. We don't have the ones for this session yet, but they will be uploaded tonight after this presentation. But anyways, like this is like the source of truth with the presentations. You can also find the notebooks, as I was mentioning. So try to use these resources. And yeah, so as I was mentioning before, today we'll talk mainly about TTS. In 2 weeks from now, in the next session, we'll talk about PyCTC decode, which is a library for CTC decoding. This will be a presentation from the Kensho team. They are professionals working in this area, so it will be they are the creators of this library. So it will be a very interesting presentation. Having said this, that's pretty much it from my side, and I let Vivi continue the presentation.
Perfect. Let me quickly pull up my screen. I hope it's visible.
Yeah, that's good.
All right. Um, Perfect. So first of all, Happy New Year to you all, and thank you so much for tuning in. Um, so today we're gonna today is all about like text to speech. So I'm gonna start off with like talking about like more modern methods of text to speech, like more deep learning based methods of text to speech, and like later on, Vatsal would join us and like he would be talking about more like the history of text to speech and like how did we come to where we are and how can we sort of leverage our previous findings to the use cases now. um, so without further ado, let's dive in. Um, so we've seen this before as well. When it comes to text to speech, the key task is to take a text or to take a snippet of text and to get some form of an audio out, right? So if it's time for lunch, then we take the individual word tokens, it's time for lunch, and then create the corresponding audio off of it, right? um, Sounds pretty simple. And the way we sort of do this in the whole text to speech domain is by splitting this entire task into two subtasks, right? So the first subtask is that we take the text and then we generate the corresponding mel spectrogram off of it, right? And then the second task is to take that mel spectrogram and generate the audio out of it, the one that we hear, right? And these are two like individual models, right? And we'll basically look at both of these model types at a sort of high level um, in the next 10 minutes, and so on. So before we get into like how text to speech systems are, or like how do we predict a mel spectrogram, and like how do we go from mel spectrogram to an audio, let's first ask this question, like why do we think text to speech is hard? We have some text, why can't we just take say word level s- word level audios and just stack them up together to form a sentence? And with that, I would ask you to sort of say these sentences out loud for me, right? So the first one is, it's no use to ask to use the telephone. The second one is, do you live near a zoo with live animals? Um, and the third one is, I prefer bass fishing to playing the bass guitar, right? Um, you would you would see that there are like in these within these sentences there are like certain tokens. For example, in the first one, use, which has different pronunciation, right? Like the way we say that out loud is different. So it's no use um, to ask the use um, to ask to use the telephone. Like both the use, even though the text itself is the same, has very different pronunciation, right? Similarly, for the second one over here, it's much more prominent. Do you live near a zoo with live animals, right? So you can see that the first one is live and the second one is live, right? Even though like the text is exactly the same, right? In the second one, the first one, like the first pronunciation of the token is bus, and the second one is base, right? Um, and like any language is full of such instances, right? And the pronunciation is very like context dependent, right? And this is just one of the reasons why text to speech is hard. Like there are multiple other reasons, like for example, um, modeling questions, like how like the way you the way you ask a question. So let's take a very simple question: do you live here, right? um, would have a very different way of would have a very different pronunciation, like overall, like the audio would be very different when compared to just a statement: do you live here, or like I live here, right? So um like the way we perceive sound and the way we generate sound is very different, and is very context dependent, and that's what makes text to speech really hard. And we'll also see like a couple of other reasons why it is hard, but this is one of the reasons why we cannot like why we cannot just have like one audio per token and then just like stack them up together and say that this is the spoken sentence, right? So um, it has to be dependent on the neighboring tokens. Um, and the other reason why text to speech is sort of hard is the way text to speech sort of works is that we have like raw text, right? So a raw text can be something like it is time for lunch, um, and we will go for lunch at 1300 hours, for example, right? You would see that the way we write stuff is very different than the way we pronounce stuff, right? When we write stuff, we use certain abbreviations. For example, if I'm texting someone, then I will be, instead of saying hey what's up, I will be like sup, sup, question mark. When we're tweeting, we will sometimes remove vowels from the words just to meet the overall character limit and so on and so forth, right? So the written text is very different than the way we speak it, right? We use like numbers, we use like dollar amounts, euro amounts, yen amounts, whatnot, right? The way we speak them out loud is also very different, right? There are abbreviations, right? So like NYC, which is New York City, is like one sort of abbreviation, right? Then there are like dates are pronounced differently. Someone would pronounce dates like today is 4th of January, right? Or someone will say 4th of January. Someone else might say it's the fourth day of January, right? Or someone might just say it's fourth, right? And like assume that January is implied, and so on. And then we have like acronyms are supposed to be spelled out, like exactly how they are. For example, DIY, like do it yourself. DIY, like if you see DIY in a text, then you just say DIY, right? You don't just like you don't say D, which is DIY. So you basically have to say them out loud, right? And so the way our text-to-speech systems work is that we have an explicit text normalization um, step first. Like as soon as we get the text in, we first have a text normalization step, which basically standardizes all of these like non-standard words into something that can be s- um, e- easily be processed by the model, and then we can get a corresponding audio off of it. Let's look at some examples of this. So just the token 1750, like 1750, based on context, like the first one, the European economy in 1750, right? So in this particular context, I am gonna say 1750 as 1750 because it's an year, right? If I was to say the password is 1750, right? So in this particular context, I would effectively spell out each and every individual digit, right? When I'm talking about dollars, I might say something like 1750, right? If I'm just telling someone to pay me that amount, or just letting someone know about this particular dollar. But if I'm dollar amount, but if I'm writing it on a check, or like if it's something for like official business, then it would be something like 1750, right? And over here you see, like, this is just one example, like literally one example of the token 1750 um, being being sort of um, pronounced, or like being said out loud differently in different contexts, right? So we need to have like some sort of a text normalization process um, for our text to speech system, so that like we can, so that our model, one, does not get confused, and two, we have like a standardized way to process all forms of similarly occurring patterns, right? The way this is done right now in the systems is in either of the two ways. Like the first one is like using rules and regular expressions. So like every time you see a particular date, you pass the text through a regular expression, and then that date is sort of expanded to say 4th of January 2022, right? And like similarly, like for example, if there is a email ID which is put in, blah at the rate blah blah.com, then like you find at the rate, and like you the at symbol, and you say at, right? You find dot, and then you replace that with dot, and so on and so forth. So the first step is like, we, of course, we can use regular expressions. There are more modern methods which basically treat this as a sequence to sequence task as well. So like normalization as a sequence to sequence task. So it will be something like you pass in, um, say, I live at 123 Baker Street. But instead, like, I just write 123 Baker and then st dot instead of street. So then like the sequence to sequence model basically treats this as again like a sequence to sequence task, but then it takes the unnormalized um, sentence, and then like returns the normalized sentence at the end, right? However, again, this is not completely state of the art yet. It often requires a lot of post processing because we only have so much data, and models generally tend to make mistakes as well. Typically you would see in like production settings, or at least typically what I have seen in production settings is using like rules and regular expressions, and um, you know statements like those to sort of normalize text than sequence to sequence models. However, this is an active area of research. In fact, in the chapter 26, they have mentioned a couple of really advanced techniques as well, that can be used to replace regular expressions with more sort of intelligent methods as well. So now that in the entire text to speech part, now that we have normalized our text, we get to the next part, which is taking this normalized text and then predicting the corresponding Mel spectrogram off of it, right? And by and large, the architecture that we use for this is very similar to what we saw last to last week, right? With ASR, we use the same encoder decoder architecture with attention, right? So in this setup, the encoder sort of takes in a sequence of letters, right? And then like sort of processes it, and then like it gives out the hidden representations um, of the letter sequence, right? And then the decoder takes this representation, and then uses the attention mechanism um, to then further sort of predict the spectrogram off of it, right? So in principle, it remains the same. Like the task itself remains the same. In the case of ASR, we had the spectrogram going in, like, so we had the audio, then audio was converted into spectrogram, and then that spectrogram was passed to encoder, and then like decoder sort of took the encoder hidden representation, and then we, using attention, and then like we as an output we get the transcribed text, right? Over here it's basically the same except reversed, right? So now we have like text as an input, and we get spectrogram as an output. um, and um, you know let's sort of look at like one such architecture, like one such architecture type in a bit more detail, just so that we get a sense of what actually is happening over here, and like how things actually get together. So this is a Tacotron 2 model. This is from Google folks, and it for at least a while it was the state of the art. And it basically has convolutional layers, and then like in both like encoder and decoder, and it predicts Mel spectrogram, as you can see over here. And then there is another vocoding process which we'll get to in a bit, which creates the final waveforms, right? Let's sort of look into this in a bit more detail. So uh, like the at the broad level, like what's happening over here is that the Tacotron 2 encoder, it first like takes the text, and then like it creates like character embeddings out of the text, and then it passes them through um, like stacked convolutional layers, um, which essentially understand um, the the neighboring context of the input itself, and then you pass that through a bidirectional LSTM, and that particular sort of like the output of the final convolutional layer, which is like passed through the bidirectional LSTM, um, is then sort of used by the decoder, right? And then there is like a there is like a location sensitive attention involved here, um, which essentially uses previous like values from previous time steps of the input itself, and uses those and like provides that information to the decoder itself to process further, right? um, Once like in the whole decoder step, you can see that there is like a 5 convolution layer postnet. Like this basically takes the input from encoder, and then there is also like a 2 layer prenet, um, which essentially does two things, right? So one is that it does something known as a stop token prediction, which is that given the current sequence. So say for example the sequence is it's time for lunch. So given the it's time for lunch sequence, if we're at lunch, then it basically predicts whether or not should we like stop predicting the spectrogram or not, right? So it does like a stop token prediction for each and every step, and then um, parallelly it would also sort of append the previous spectrogram, like the previously generated spectrogram with the current step, and then like generate the new spectrogram and so on. And this sort of keeps on happening time and again through all the steps, and like through all the data that we feed to it, right? um, the data set that essentially goes through Tacotron is nothing but audio files, right? Like audio files and like the corresponding text to it, right? Um, so essentially, we can like if we take, for example, the most used English corpus, which is LJ speech, then you have like a couple of novels which like someone basically dictated through, and then we basically take sentence by sentence audio files off of it and the corresponding text, and that is what is essentially fed into um the model itself, right? So um, like key takeaways from here is that like you have like an encoder decoder architecture, and then like you use previous time steps to predict the next sort of spectrogram, or to predict the current spectrogram, right? So and that's how it will also function in like production setups as well. And like once we have the spectrogram, then we have the whole vocoding process, which we'll just get to in the next slides. I know I kind of like skimmed over the entire Tacotron architecture in like last 2 minutes or 3 minutes, which is not that sufficient. I do agree, but I will send like couple of links to like slides which explain them in detail, and like also in the SLP book chapter 26 they explain it um, in um, in a bit like high level fashion as well. So you can also look into that. Um, Now, so just a quick, just a quick primer. So up until now, we did some sort of text normalization on on our text to make it more um, um, ready to convert into audio, and then we had the whole text to MEL spectrogram um, conversion, which was done through Tacotron. And now that we have the spectrogram, we have to sort of convert this back into the waveform, right? This entire process is called vocoding, and there are like multiple vocoders. The one that was used in Tacotron 2 architecture was specifically called WaveNet, and like the way WaveNet sort of worked is that it takes the spectrogram as an input and then produces sequences of 8-bit audio. Um, and it essentially has like, I think I have the, one second, sorry about that. It essentially has like, it essentially uses like these dilated convolutions, like which is that you take like um, sort of piece by piece information, you sort of combine them together through like all the hidden layers, and then you eventually um, get to the output, and like it uses these to then sort of convert the spectrogram into audio, right? And the output of these dilated convolution is then like passed through like a softmax, which makes a 256 way decision, because we're converting into 8-bit audio. So 8-bit audio means 2 to the power 8 would only have, for like at an any given at any given point of time, there can only be, a value between there can only be 256 sort of values over there. So we pass this through softmax, like a 256 way softmax, and we get the corresponding value, right? Typically you would see that the audio that we are used to hearing is 16 hertz. um, there is a 16 hertz model as well. 16 hertz would essentially mean 65,536 way decision. But the one specifically used in Tacotron 2 was an 8-bit one. And yeah, again, like this was just like a brief overview of what WaveNet does. I will send through like more detailed slides on slides plus resources on both WaveNet as well as Tacotron 2. Um, Now we get to sort of the second last slide, which is the overall evaluation. So how do we actually evaluate text to speech? So one of the most go-to ways is through mean opinion scores. So which is that you basically have a lot of synthesized utterances, and then like for say for example for 2025 samples, you create the audio files, and then you create a survey, and then you send it over to people based on how you design your study, and then they um, give it a rating from 1 to 5, right? On like how natural does the synthesized voice sound, right? And then you get to some sort of a score through that. This is something that is used like for pretty much all architectures, pretty much like is kind of like the industry standard. um you can also run like A/B tests. Say for example, if you are on the Alexa team or on the Google Assistant team, and you want to see which model performs better in synthesis, then you can have, you can have sort of utterances, or like the synthesized sound, or like the audio files of both the systems, and then you can have human listeners sort of judge which one's better and which one's not. So this is also used quite a lot often when it comes to um, you know testing which model performs better, and so on and so forth. um, then this is this is the last slide before we dive into some code. So there are like multiple types of models. So for like text to speech, for like text to spectrogram models, there are attention based models like the one that we covered, which is Tacotron. There is also like duration based models, which are which is fast speech, which do not depend on self attention. Um, and then there are like for vocoding, which is spectrogram to waveform, there are autoregressive models like WaveNet, which use prior information to predict the next. There are flow based models and there are GAN based models. In my experience, GAN based models are like supremely better um, than at least autoregressive ones and flow ones, but then again, it depends from language to language as well. Um, okay, so that was a lot of talk. Let's quickly see how we can see some of these text to speech models in action. Um, so let me quickly move to the collab. I'm not gonna like run this through, but I will like this entire notebook would be available on the GitHub repo that we have, and so you can basically just open it as a collab. And what we do over here is we use the TTS library from Coqui AI, and they have a lot of pre-trained models already available for you to try out. And they also have like really nice fine-tuning guide that you can use to fine-tune the models on your own data as well. So I really like their interface and the overall way that you can quickly get to testing out different models and fine tuning them. Um, Really nice library, would recommend. Um, so we just installed TTS and um, then like let's look at what kind of models they have. So if you look at their list of models, they have a lot of English models. They also have French models. Mandarin models, German models, um, uh, Japanese models, and so on. And they not only just have like text to spectrogram models, they also have vocoder models. So again, for like English, German, and you can see that they have some GAN based models, and they also have n- autoregressive models as well, and so on and so forth. Um, and Yeah, so you can essentially take any model from here and essentially mix and match them and try out on your own data set to see like how it works, right? So let like for example, we can just quickly test the model that we looked at, which was Tacotron 2. It takes about 2 minutes to set up on Colab. That's why I ran it before, so that we don't have to run it right now and don't have to wait. Um, but it basically loads up the entire model and then like passes the text through it and like saves the audio file within Colab, and it sounds something like this.
Today is a good day. Today is a good day.
I hope you were able to hear that. And I don't know about you, but this sounds pretty good to me. Just given that we're just using like a pre-trained model, and it does a pretty fine job, pretty good job straight out of the box. Um, and with that, I would leave an exercise for you, which is take the three sentences that we spoke about in the presentation itself, and you know try your own model. Try different models from the TTS library itself, and see which one performs the best and which one is able to capture all the patterns that we spoke about, right? And let us know in the Discord chat. You can also play around with different vocoders. Sorry, this should be vocoder, but you can also play around with different vocoder names and like vocoder models to see like how the model is, or like how the model is performing, and like how the overall sort of combination of text to spectrogram plus spectrogram to audio sort of works. um, Last but not the least, I know I'm about like a minute over time. You can also go over to like Hugging Face Hub, of course, and you basically want to be able to click on the side and like go on in within audio, go on text to speech, and you can see like all the different text to speech models available over here. So this is there is like from Facebook fast speech 2 model trained on LJ speech. Then there is the end-to-end WITS model by ESPNet team, and so on and so forth. So you can essentially take any of these. Let's, for example, look at the fast speech 2 model and just typing anything right now, and you can essentially try that out. And in most cases, you can also see like a code snippet on your left side, which you can basically just copy and paste and then be able to run in your collab or in your own environments to be able to see how it goes. All right, I'm not gonna wait for this to load up. Or maybe,
Hi, my name is Adam.
okay, that did not sound that well.
Hi, my name is Adam.
But yeah, you can basically try out different models and see which one fits your um, needs better. So, all right. So with that, I will pass it back over to Vatsal.
Awesome. Thanks a lot, Bibi. Some people were asking, we'll share the notebooks later today, so you can try this out directly. And having said that, at the end, we'll spend some minutes answering some of the questions. But now I would like to introduce Vatsal. Hey, Vatsal.
Hey, how's it going? Can you all hear me?
Yeah.
Yeah, perfect sound. So we'll let you introduce yourself and we'll remove ourselves from the presentation. Again, thanks a lot for joining us.
No worries. Thank you. So hi everyone. I'm Vatsal. I got into speech in just a quick intro. I got into speech in 2017. I was doing very pure maths, and one night I sat down and tried to generate speech for a blog post that I was writing, and it sounded really bad, and that really annoyed me. And I wanted to fix that problem, and I came across this paper called WaveNet. And at that time, I didn't know any machine learning, but the WaveNet sample sounded so good that I wanted to synthesize my blog post in that voice. So I ended up spending my time, almost all of it, learning machine learning, and then implementing WaveNet, and then one thing led to another. And then I ended up at Amazon as a scientist, where I helped build some of this technology that we mentioned, and also spent 3 years researching improvements on it. So yeah, a big speech fan. Happy to help anyone. If there's anything you want to get in touch with, any questions you have, feel free to DM me. My Twitter DMs are open. And if you have any feedback, I love to hear feedback. So my website is always open. All right. So what will we be talking about today? So I just want to give a quick journey of like speech synthesis from when it first started. This presentation is hugely inspired by the person who got me into speech. His name is Andrew Green. He was my manager at Amazon. And it really gives a good high-level perspective in where we're headed and where we're coming from. And I found it very helpful, and I wish I'd seen it earlier. So I just wanted to share that with other people who are going on this journey as well. So I just want to start out with, what are we trying to do with speech research, or when we're trying to create speech? There are 5 or 6 things that we care about. The first 2 were sort of like the focus for the initial part of the research, which is something called naturalness, which is when you synthesize something, how close does it sound to being human? Then the second part is intelligibility, which is when you synthesize some speech, can you understand the words that are being said? The third part is prosody or expressivity. So you have some text, but the text can be said in a sad context or a happy context. So this is about understanding what the emotion of the text is, and then being able to synthesize the audio in that emotion. The fourth one is amount of data required, which is, we used to take tens of hours of data to create voices, and it's down to 10 or 20 minutes now. And with that comes a lot of research into ethical use of these models. And the final one is adaptation to situation. So as you're noticing now, there's some things that I'm stressing and I'm going slower, and there are other things which I'm moving faster. And how do we get speech synthesis models to be able to adapt to the situation and read that situation? And that's like the broad goals that as a community, we sort of have been following. Where deep learning fits in is sort of like making the significant progress in creating natural synthetic speech, but also enabling better flexibility. So a lot of the speech before the current deep learning models sounded very monotonic. And what deep learning really allowed us to do is get people to speak in new languages, speak in new emotions. And so I just want to show that journey to everyone today. So I'm just going to start out with some fun facts. This was literally the first thing that happened in 1928 by someone called Homer Dudley. So this is a vocoder, which stood for voice encoder, and you might have seen these words before. And this is basically a physical machine which took what you were saying, split it into its spectrum, and then synthesized it back. And this was 1928, so this was not really a voice synthesizer. But then what Homer Dudley did at Bell Labs is replace this like initial portion that you have where a human is speaking into something and replaced it by someone who's sitting there and like moving keys. And this happened in the 1939s. And it was the first like voice synthesizer that we ever had. And it wasn't exactly text to speech because you can type in text, like you needed a human to control it. But it was the first time that we actually got generated speech out. So now I just want to show you where we went from here and also what this sounded like. So I'm going to play quite a few examples. So let's start with the voder, which is the thing that I showed you with the pedals in the previous photo.
Suppose you sing a song for us, will you?
Yes, certainly.
Well, how about Old Lang Syne?
I'm okay. She's on the flavor before I never going on. She's on the flavor before I
I always love that demo. It really makes me smile because this happened back in the 1939s. And I just love that. But there was literally someone sitting down and like pressing keys, trying to make that happen. And people had to be trained to actually be able to use that. I'm going to play another example from the voder.
Now will you have him repeat that in a high voice?
Greetings, everybody.
And now in his best bass.
Greetings, everybody.
So I just wanted to show a couple of examples there. The first one sounded very good, and I just wanted to show, a different example where it didn't sound that good. So this happened, but we couldn't really go from text to speech. And the first time that really happened was 1980s. And what we basically did is we took a physical understanding of how voice production works in humans and try to copy that in software and hardware. And this was called formant-based TTS system. And what it sounds like, you might already be familiar with from Stephen Hawking's voice. But I'm just going to give an example of that.
I am the standard male voice, perfect all.
This is the result of trying to imitate a female voice by increasing the pitch, reducing the head size, and lengthening the open quotient.
Yeah. So pretty good, right? But I think the main thing to notice there is both of those sound really intelligible, but they don't really sound natural. I think like there's this like feeling when you hear it that, it doesn't sound like a real human. And that's basically the problem that we've been trying to resolve since the 1980s. And basically the idea that came in 1990s was along with smartphones coming out, and we had to do encoding of audio for smartphones. And people basically figured out that, hey, instead of trying to generate sounds, why don't we just pick sounds that already exist? And this is what was called concatenative. And so what people did is use encoding techniques to encode like small units of audio. And then when they wanted to synthesize something new, they would use those encodings to try and pick these units, stitch them back together, and play something. And we got really, really good at it. So I'm going to show you an example.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
Right? That sounds intelligible and that sounds natural. And so it's a big jump from where we were in the 1980s. And then the big jump that came in 2018 with the Vaibhav and Tacotron papers were, we sort of know how to sound natural, but because we're only picking speech units from a database, we can't really do something different. Like, most of the speech units or the corpora or the databases that we had really natural sound, like monotonic, like calm sound. So you want someone to sound happy or excited or sad. There's just no way of doing that. And so what WaveNet did for the first time was be able to go back to what we were trying to do in the 1980s, which is actually generate units of sounds rather than picking them. And it managed to do that with deep learning. And sorry, I'm just going to play an example of that now.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
Yeah. So notice the difference there is slight, but it's there. There's a huge quality improvement. But the big thing is really what it gave us in terms of flexibility. And I'm going to just dive further into why that's important and, try and nail that point home. I'm also just going to dive into this like little bits of pieces that happen at the end, from concatenative speech to deep learning, and how we actually got there. So this is the point that I was stressing earlier. So let's say you have a sentence and you go to some phonemes, like you have sentence, so you split it into s, and x. So what we initially used to do is, okay, we need these phonemes. What we're going to do is just search for them in our database, concatenate them together, and put out a sentence. And by search, I mean literally search. You just like look at all the, like, imagine you have like each of these phonemes. You just go through your database, see whether they match, and just take them out. Then we said, okay, why don't we search in a smarter way? And this is where hidden Markov models came in, and then neural networks came in, and that was called hybrid speech synthesis, which is combining neural networks to pick these units. But the problem was always that, if you don't have the sound, you can't put it out. If your databases are composed of calm sounding voices, you're never going to be able to sound excited. And this was like the big block that we could never get over. And this is what end-to-end deep learning really fixed for us. So this last bit of picking the sounds, instead of picking sounds, we're generating sounds now. And again, we were trying to do that in the 1980s, but we just didn't have the tech to do it at that point. Just to go into it further, just to summarize very quickly. So what unit selection or hybrid really enabled for us was this naturalness. We could be very natural, but not really flexible. Then we had this older technique, which allowed us to be flexible, but not really natural. And then this is where we currently are, which is deep generative models, and this is where humans are. And with deep generative models, what we're really seeing is this naturalness and this flexibility, and we're started to see that with things like your TTS, which was mentioned on the Discord channel, where you can say something once in a given language and get you to speak a new language. You could do things like create models or create synthetic voices with 10 minutes of data. You can do things like get someone to sound excited or sad. And all these things that we couldn't really do with unit selection, we can start to do with deep generative models. There's still a gap, and the gap is really coming from the fact that we spent 40, 50 years researching these things, but it was so focused on concatenative speech synthesis that most of the data sets that we have were tailored for concatenative speech synthesis. So that means that they were all very calm sounding and natural, and didn't really have the kind of expressivity that we're looking for. And so that's why, even though we have better tools, we've sort of been going through this phase of getting the right data so that we can use these machine learning models to the full extent and utilize the potential that they really have. So we're not really there yet with the deep generative models, but it's largely a case of finding the right architectures and getting the right data. And that's where the field has been looking to. And that's where I think we're headed in the future. So that's it. It was just a really, really quick presentation. I just wanted to give a very high level view of where we've come from, where we're headed, and where we are. And I hope that was useful.
Awesome. Thanks, Vatsal. I think that was quite insightful. So thanks a lot. All right. So we have a couple of questions, both in YouTube and in the forum. If you're in YouTube and you haven't asked any questions, you can go to Discuss, and we'll spend the next 10 to 15 minutes answering any questions that you might have about DTS, or if you have any specific questions from Vatsal's presentation, that would also be great. But I think we can dive directly into it. So the first question that was asked in Discord was, if I want to train a TTS model on my own speech to imitate my voice, what amount of records do I need to make for training a model with good quality?
I think I can probably take a stab at that, because I was doing some research the other day on that. CoQAI team released your TTS yesterday, and what an opportune time to release that. And it's what they have, like a collab demo, and we can link that in the response as well. And you can basically just upload one sample of your own voice, and it is able to imitate the voice or sort of understand the way you speak by and large, and you're able to sort of convert the audio in such a way that it sounds more like you. So they have open source their model, so you can also use that, and it is available in the same Colab notebook that I showed you earlier as well. So you can use the same model over there as well, and they also have a really nice demo put up on their website, which I think Omar is showing right now.
Yeah.
Um, as well. So to answer your question, that and at least according to them, you can get reasonable response, like reasonable results with just one audio sample as well.
Yeah. Sorry, I would just quickly add to that. Like, it really depends on what you're trying to do. So like I mentioned, like, we were in this world of concatenated speech synthesis for like 30, 40 years, which means a lot of our data sets are very like calm sounding neutral voices. So, if you want to synthesize speech that sounds happy, I don't think you're going to be able to put a 1 second of your speech there and get it there. Or like, if you want to be able to synthesize your podcast, you're not going to be able to do that. So it really depends on what you're looking to do. Happy to feel free to DM me or chat on the Discord about this, but like it's a great place to start, but it's heavily dependent on what you want to do. If you just want like a neutral voice that kind of sounds like you, this is like a great place to start, and it's amazing that they've open sourced this. It's very exciting.
Awesome. Thanks a lot. Yeah, next question is, should I fine tune a pre-trained model, or should I just train one model from scratch?
Yeah, I mean, I think we've now reached a place wherein like training from scratch, unless you have like a lot of data available for your use case, then only it is recommended. But I mean, you should pretty much always start off with pre-trained models. That's what I would personally recommend. Again, as Watsal also recommended, mentioned before, this also depends on like which language are you trying to sort of synthesize the speech in, right? So for example, if it's in English, we already have a lot of very good fine-tuned model, very good pre-trained models available for it, right? But if you talk about sort of more obscure languages, like in fact, even just if you talk about Hindi, or if you talk about even for like German, there are not that many models available which you can fine tune on as well. So depends on what language you want to synthesize in, and like second, depends on what exactly are you synthesizing as well. But more often than not, fine tuning a pre-trained model is generally the first place to start with. Yeah.
Cool. Let me put one question from YouTube as well, so we have a bit more diversity in the questions. Is how do you evaluate MOS in a non-supervised way, like an estimated MOS? I don't think. I mean, TTS in particular is hard to evaluate because it's very subjective, right? It's not like as easy compared to uh, audio to text, right? In that case, it's a bit easier to compare like the ground truth. But when you're generating synthetic speech, I think it's very valuable to have humans in the loop that are able to actually evaluate it. But I don't know,
Yeah, I
maybe
mean,
there's some work on this.
yeah, just a quick thing on that. I mean, you can also use something like a MOSNet, which basically takes the synthesized speech and like gives you a MOS score at the end of the day. And it is basically a predictor of mean opinion score. Again, it has its own like caveats. So I'm just sending this on the private chat. The link to the paper. So you can definitely use something like that as a starting point. But again, it has its own demerits, which is that it is only as good as the MOSNet itself, right? And like and say for example, if the data on which your MOSNet is trained on, and if the data on which your text to speech system is trained on, you would are different, then you would by default get like a lower score, which is not desirable. Uh, although, like, that being said, just a quick rant. I do not like mean opinion score that much, either, because it's very subjective to people. And you would see these, like, insanely amazing papers, and like architectures out there with just like one evaluation criteria, which is mean opinion score. We do need something better, but yeah, I haven't come across anything else, to be honest.
So one thing that works quite well is Mushra. In case people haven't seen that, usually gives better results in terms of finding out. Other than MossNet, it's just something to be aware of. Like it's you should be clear on what you're evaluating. So as I mentioned, there's some goals around, like, do we care about naturalness? Do we care about intelligibility? Are you solving a task which requires emotion? So is the emotion there? So MossNet can't really get all these things for you. So it really depends on what you're doing. At the end of the day, it's like an what do you call it? We don't have objective criteria for what makes speech good. If we did, we would probably put that in the laws, right? Like that is that's the holy mecca. That's really what we want to be able to do, and we can't do that. So I think if what you're trying to do is build a good speech synthesis model that sounds good, you're going to have humans test it. There's no loss for that. The only other thing that I would mention is something called the free shade distance, which you can treat your ML spectrogram as images and compare the loss on that in a subjective way. And this is used in the image synthesis community, so that can be applied in speech as well. But yeah, it's again something that as Vaibhav said, this is really something you should do subjectively. And Moss is not perfect, but it's still very, very useful.
Yeah, and just wanted to, like, quickly point one quick thing out, right? So you can also, like, tweak your Moss survey based on your criteria. So say, for example, if you just want to look at the whether your model understands certain prosodic patterns or not, right? It can be informational, or it can be sort of question based, like whether when you ask a question, whether there is a difference in pitch or not, right? If you just want to, like, look at these, like, really small fine grained things as well, then you can just change the way you provide information to the surveyor, or like the person who's evaluating it. And you can give them, like, question answer responses. You can give them prior context, post context, so on and so forth, for them to judge it in a more sort of comprehensive way. But yeah, just wanted to put that out there. Yeah.
And if you're looking for a service, I've used Amazon Turk in the past, Mechanical Turk, and that costs like $10 an evaluation around. So if you are looking to do that, you could do that. I mean, I don't know, is $10 cheaper than running a deep learning model multiple times and getting bad results, or is this just running an MTurk Moss for $10? I'm not sure. It depends on you and what you're doing, but yeah, MTurk is always an option.
Cool. Yeah, and this, like, a follow-up question is what architecture. Oh no, sorry. So this was related to the question about fine-tuning a pre-trained model or training one model from scratch. Aberki was asking what architecture and instrument would be better to use. I don't know if any of you have any specific suggestions here.
I don't have, like, a specific suggestion, but yeah, I mean, you can, like, I personally, for my stuff right now, I'm just using, like, the base transformer text to speech model. But like, it is for a very different use case. I would say you can never go wrong by starting off with, say, fast speech. Fast speech is pretty good. Or in fact, like Tacotron as well. I haven't tested out, like, end-to-end text-to-speech models like Wits so far, so I don't know, like, how their performance is. But I think typically you cannot go wrong with something like fast speech, for sure.
Cool. We have two more questions. The first one is this one. Is English pre-trained model good for fine-tuning on other languages, or it's necessary to find the model trained on the same language as the target one?
Yeah, maybe I can just give a quick thought on this, and Vatsal, feel free to add on that. I have never sort of used, like, an English pre-trained model on any other language, because intuitively it never made sense to me. Because different languages have, like, different different rules, right? So I think I gave an example on Discord the other day that just the word, for example, 25, right? So 25 is 20 and 5 in English. And if you look at it in German, it is 25. So it's 5 and 20, and so on. So the way we sort of um, talk or like just the rules of the languages change a lot, right? So I like maybe if the languages are like very close, you can give it a shot, but pretty much always almost always you should either find like a multilingual model, or just look for a model which is in the same target language in itself.
Yeah, I would say I'm not sure what would work better, but I would if you're telling me your option is like no pre-training and English pre-training, and you want to use it on Mandarin, I might still use the English pre-trained model. And the reason I have for that is, so there are two components, right? So one is the text to melt spectrogram, which is the encoder decoder, and then you have the vocoder, which is melt spectrogram to waveform. If you look at the melt spectrogram to waveform problem, like, there's probably things that even for an English recoding task that could be useful for a Mandarin recoding task. At the end of the day, you're adding phase back, and we've seen things like universal vocoder, which work across multiple languages and things like that. So that definitely sounds like there's some information there. And even with the encoder decoder, it sounds like a big part of the decoder is going from like latent representations of that like text to melt spectrogram. Again, that sounds like something that could be useful, but probably the encoder being useful, I can't imagine that, because the text that you have to convert to latent space is very different. So yeah, it depends. Like if you have very little data and you only have like an English model and you want to train on French, probably what I would do is start out with like pre-training only the first few layers of the encoder and keeping everything else fixed. But the more you can fine-tune, the better. It's the usual like fine-tuning strategies apply, but like cross-lingual fine-tuning does work, and there's obviously like relationship. There is information there that can be carried over to a new language. So it's not worse than starting from scratch, but it's not as good as having a model in the language you're looking for.
Awesome. Thanks a lot. We're already in time, so I think we can close this for today. There are no more questions in the forum. If there are any remaining questions, I would suggest you to ask them here in the forum or ask them in Discord. Ideally, in Discord, we'll be sharing more resources on this. We'll talk a bit more on this topic, so feel free to propose any topic to discuss. If you would like to see any presentation on a specific topic, for example, these techniques applied for music, for example, feel free to propose them either in Discord or creating an issue in the GitHub repository. I don't know, maybe if you would like to add anything else.
Yeah, just want to say that we typically like sort of collate all the responses to all the questions by like tomorrow noon. So if you have any more questions, feel free to put those along, and we will sort of collate like one mega answer with all the links, all the responses, and like everything. So do that, and yeah, just want to double down on what Omar said. Create an issue on the repository if in case you want us to find someone to speak about a particular topic, or if you yourself want to speak about a particular topic in the next coming weeks. We would love to help out either way, for sure.
Yeah. Yeah, and then see you everyone in 2 weeks for the PyCTC decode presentation. Thanks a lot, Batsal, and thanks a lot, Bibi, for the great presentations. And see you everyone in 2 weeks from now. Thanks a lot.
Bye. Ciao, ciao.